Alright, so in 6.5 we're going to continue talking about radians. So as we've been talking about, we have the arc length of a circle. And if theta is in radians, then the arc length is S is equal to R times theta, where S is our arc length and R is the radius of our circle. So in terms of a picture, we would have our circle. Here's our radius R, and we have some angle theta. And then we would have our arc length S, which is the distance along the outside of the circle, and we have an R. So we've been talking about how radians are the natural measure. Well, if theta is measured in radians in this, we know from our equation that we have S is equal to R times theta. Well, if we solve that equation for theta by dividing by R, we get theta is equal to S divided by R. And if we do some dimensional analysis, S is going to be measured in some units of length, and the radius is also going to be measured in some unit of length. And then our units would reduce out. So what that means then is theta is a unitless number. So this gives that theta is a unitless number. And this is why radians are preferable, is they're not a derived unit. They are just a pure number, so the set of real numbers. So this leads into the topic for our next section, or for this section, which is that the domain of a circular function is the set of real numbers, radians, and we call all of our trigonometric functions with domain all real numbers circular functions. So then, for each of these, for sine and cosine, we're going to have, our domain is all real numbers, but when it comes to tangent, tangent is defined to be y over x, or sine over cosine, and we know from our unit circle that cosine is equal to 0 at all of the half multiples of pi over 2. So theta for tangent cannot equal plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. for all angles. Alright, so the next thing we want to talk about is even and odd functions. So if we think back to chapter 2, it's been a while, we had some definitions for each of these. So a function is even if the following is true. So even functions were symmetric with respect to the y-axis. And in terms of symbols, that meant that f of negative x was the same as the negative of f of x. For odd functions, we had rotational symmetry with respect to the origin. And in terms of symbols, this meant that f of negative x was equal to negative f of x. So let's analyze each of our functions independently. So if we were to take a look at the unit circle, let's draw the axis first. When we have our unit circle, if I take any point out here, x comma y, and then I'm going to have some angle theta, if I replace theta with negative theta, I would have something down here. I would have a rotation of negative theta. Well, if I do that, what is going to happen to my xy coordinates? Well, x in quadrant 1 and quadrant 4 are the same, but in quadrant 1 and quadrant 4 we have positive y and we have negative y. So if I were to analyze this, and if I look at the sine of theta here, so the sine of positive theta is going to be equal to our y value. So the sine of positive theta is going to be positive y. And if I look at that same circle and I ask, well, what is the sine of negative theta? Then I'm going to get negative y. If I substitute this into that equation, I would get then that the sine of negative theta is equal to, this minus sign comes straight down, and I replace y with sine theta. So then this tells me that the sine of negative theta is the same as the negative sine of theta. So I look back at my definition, and that is exactly this right here. So this tells us that sine is an odd function. So that means sine is going to have rotational symmetry with respect to the origin. All right, so based on what we just did, it's now your turn. So determine if cosine is an even function, an odd function, or neither. And we're going to need to do the same thing, so you're going to want to draw or use that same diagram to determine sine theta, or cosine theta and cosine negative theta. All right, I'm going to break us up into... All right, so we want to determine if All right, we want to determine if cosine is an even, odd, or neither function. So I'm going to draw that same diagram again. And if we look at positive theta and negative theta, and we analyze our points once again, we would have x comma y, and we would have x comma negative y. That would give us that the cosine of theta is equal to x, but the cosine of negative theta is also going to be equal to x. And then if these two things are the same, that would give us that the cosine of theta is the same as the cosine of negative theta. So that would be, by definition, an even function. So it turns out that sine is odd and cosine is even. So turns out we have some properties of even and odd functions that will be helpful when it involves products and or quotients. So for products and quotients of even and odd functions, we have the following. So even functions behave like positive 1, and odd functions behave like negative 1. So if you have an even times an even, it's always going to be even. If you have an even times an odd, you're going to get an odd function. If you have an odd times an odd, you're going to get an even function. So using this, we can figure out if tangent is even or odd. So we know that tangent theta, by definition, is the same as sine theta over cosine theta. And from what we just saw, we know that sine is odd, and we know cosine is even. So an even divided by an odd, that's going to be this case right here, is going to be odd. So that tells us, by definition, that tangent theta is going to be an odd function. All right, well, let's go ahead and take a look at the rest of these examples. So we actually just did A. Our instructions were determine if the function is even, odd, or neither. So let's take a look at B, C, and then you guys are going to get a U try D. So if we analyze each of these, so if we take a look at x cubed, is x cubed going to be even or odd? Well, that's odd. And then we have sine x, which we just found out was also odd. So an odd times an odd is going to give us even. So x cubed sine x is going to be an even function. Similarly, we have our x squared, which is going to be an even function. And we have our cosine x, which is going to be an even function. And an even times an even is going to be even. All right, so I'm not going to break us out into rooms for this one, but let's go ahead and do our U try. So f of x equals x times sine x times cosine x. And let's determine if this function is even, odd, or neither. All right, so if we take a look at this, so x is going to be odd, and then sine, as we've talked about, so sine x is going to be odd, and then we have a cosine x, which is going to be even. So an odd times an odd is an even, and then an even times an even is going to give us even. So we're going to end up with an even function. So, like I said, the way I like to remember this is odd functions behave like -1 and even functions behave like +1. So -1 times -1 times +1 would be a +1, so that would be an even function. All right, so let's take a look at our next example. So we want to use the unit circle to plot the graph of sine theta and cosecant theta. So remember, there is a copy of the unit circle inside of Blackboard, which will be helpful. So remember, on our unit circle, we're actually going to have two different things. So the front side's got some trig identities. We'll talk about those in chapter 7. And then on the back side, we've got this unit circle, which is going to be helpful. So we want to use our unit circle to plot this function. So we're wanting to graph sine, and by definition, remember, sine is the y coordinate as we go around the unit circle. So then the sine of 0 is going to be 0. The sine of pi over 6 is going to be 1/2, then root 2 over 2, root 3 over 2, etc. So that's where we're going to get these values when it comes to graphing pardon me, by hand. So let's go ahead and approximate some of these values. So we have theta and we have sine theta. So we know that the sine of 0 was 0 from our unit circle. We have the sine of pi over 6 is going to be 1/2, right? So we go to pi over 6. The y value is 1/2. The sine of pi over 4 is going to be square root of 2 over 2. And we keep going. Pi over 3 is going to be root 3 over 2. And then the sine of pi over 2 is going to be 1. And then we have 2 pi over 3. It's going to give us root 3 over 2. 3 pi over 4 is going to give us root 2 over 2. And then 5 pi over 6 gives us 1/2. And then finally we get to pi, and we get back to 0. So let's go ahead and draw that first little bit of our sine function. And to help us out, root 2 over 2 is about 0.7. Root 3 over 2 is about 0.86. So we're going to about 0.86 and about 0.7. So if we plot these points, we have that the sine of 0 is 0. At pi over 6, we get 1/2. At root, or at blah, blah, blah. At pi over 4, we get 0.7. And at pi over 3, we get 0.86. And then at pi over 2, we finally get 1. And then we count back down. So the first part of our function looks something like this. Helps if I put all my dots in the right place. There we go. And then if we continue filling in our table, we have theta, we have sine theta. I'll put pi here because it corresponds to 0, but mostly because I want to show a pattern. So if we keep going around our unit circle, we're at pi, our next angle is going to be 7 pi over 6. And in quadrants 3 and 4, we'll notice that our y values have become negative. So in quadrants 1 and 2, sine is always positive because y is positive. In quadrants 3 and 4, sine is always negative because y is negative. So at 7 pi over 6, we get a negative a half, negative root 2 over 2, negative square root of 3 over 2, and so forth. So we have 7 pi over 6, and we get negative 1/2. At 5 pi over 4, we get negative root 2 over 2. At 4 pi over 3, we get negative root 3 over 2. And at 3 pi over 2, we get negative 1. At 5 pi over 3, we get negative root 3 over 2. At 7 pi over 4, we get negative root 2 over 2. At 11 pi divided by 6, we get negative a half. And finally, we've come full circle, and we're back to 2 pi, and we get 0 again. So we'll notice that the values between 0 and pi and the values between pi and 2 pi are almost exactly the same. The only difference is between 0 and pi, all of our y values are positive, which we saw because they're in quadrants 1 and 2. And then all of our y values are negative because they're in quadrants 3 and 4 between pi and 2 pi. But we'll notice other than that, they are exactly the same. So we finish our graph, and we get pretty much the same values. So a half. And we get something that looks like this. So that would be the graph of f of theta equals 2 sine theta. And if we go back to 6.1, where we talked about the definition of cosecant, remember cosecant of theta is 1 over the sine. So it's this same thing, but we're taking the reciprocals of all of these values. So let's grab some easy ones. So if we take the reciprocal of positive 1, we get negative 1. If we take the reciprocal of negative 1, we get negative 1. And if we take the reciprocal of a half, we get 2. And if we take the reciprocal of negative 1/2, we get negative 2. And we're going to get some of these other values in between. But then the other thing we notice, if this is 1 over sine, anywhere sine equals 0 is going to be a vertical asymptote. So our graph has a vertical asymptote here at pi and at 2 pi. So our graph is going to look something like this, getting close to our asymptotes, and similarly it's going to do something like this. So those reciprocal functions are going to have vertical asymptotes anywhere sine was equal to 0. So the vertical asymptotes of cosecant theta are at any angles coterminal to 0 and pi. So at x equals plus or minus pi times n for all n. If we look at our unit circle and we start trying to graph cosine, we notice that the cosine of 0 is 1, and we notice that it changes sign at pi over 2, and then the cosine of pi is -1. Cosine of 3 pi over 2 comes back to being 0, and then the cosine of 2 pi is back to being 1. So kind of connecting all of this with a smooth curve gives us something that looks like this. For our secant this time, similar to what we had in the previous example, we know it's going to have a vertical asymptote anytime cosine is 0. Well, cosine is equal to 0 at the odd pi over 2 multiples, so here and here. So our cosecant is going to be the reciprocal function, so it's going to look something like this as we start graphing it. So let's go ahead and grab our graphing device and check this out a little bit. So go ahead and turn our calculator on. Make sure, once again, that you're in radian mode and not in degree mode. If you try to do your graph in degree mode, things aren't going to work out. So we go cosine x in our calculator. And remember, on our graphing device, we only have sine, cosine, and tangent. So if we ever need to graph secant, cosecant, or cotangent, we have to do the 1 over, so we go grab our fraction. So we would do 1 over cosine. And now if we graph, there's our cosine function. And we're going to get, you can see our asymptotes and what our cosecant, or our secant, is going to look like. And if we change our window to match what we have here, we have 0, we have 2 pi, and then on this it was -2 to 2, and our y scale is on this, what, 0.2s? And so there's our cosine, just like we saw, and then here's our little chunks of cosecant, like we saw, coming in, and we have our vertical asymptotes occurring at the zeros of cosine, as we thought. Alright, so just remember, our graphing device is only ever going to have sines, cosines, and tangents. If we need secant, we have to use 1 over cosine. If we need cosecant, it would be 1 over sine, and cotangent would be 1 over tangent. Alright, so let's take a look at our next definition, which is we want to talk about periodic functions. So a function is periodic if there exists a positive number p such that f of x plus p equals f of x for every x in the domain of f. The smallest value of p is called the period of the function. So based on our unit circle, what would we guess the period of the sine function would be? Well, if I go around my unit circle, when would I start repeating my y values. So they're positive, 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 positive. Then they switch to negative, 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 negative. I come back around here. And then after I've gone around the circle once, what happens? I start getting the exact same values again. So it's worth noting that we have that the sine of x is the same as the sine of x plus 2 pi. And we get the same thing for cosine. Cosine x is equal to the cosine of x plus 2 pi. And x plus 2 pi are coterminal angles. So we're going to note here that both sine and cosine have period 2 pi. The next thing we need to define is the amplitude. So the amplitude is defined to be 1/2 times y max minus y min in absolute values. So for both sine and cosine, based on what we did above, what's the biggest value that ever comes out of sine? 1. And what's the smallest value that ever comes out of sine? Well, that's -1. And if we look at cosine, we get the same thing. Its largest value is +1, and its smallest value is -1. So for both sine and cosine, we have 1/2. The absolute value, y max is 1, minus y min is -1. So we have a minus minus, which gives us a plus positive. So that is 1/2 times the absolute value of 2. And the absolute value of 2 is just 2, so 1/2 times 2 is 1. So both sine and cosine have amplitude 1. So we have a few properties that we want to write down for sine and cosine in closing for this section. So we have sine theta and we have cosine theta. So some things we've noted about each of these. So the first thing that's worth noting is that they are both continuous. We took note that each of them have period 2 pi. Three, since they're both circular functions, they both had domain all real numbers. And 4, as we just did when we were talking about the amplitude, they both have range from -1 to 1. And as we just saw, they both have amplitude 1. So far, sine and cosine seem like they're exactly the same thing. They have all the same properties. There was one thing we did talk about today that differentiates them. And that is the fact that sine is an odd function and that cosine is an even function.